All right. Now that we've kind of looked at our data and we have fit our model and we're beginning to think that this may be the correct approach, let's go ahead and do exactly what we would do in every other linear model. And that's do a significance test to see if the association between our covariate of interest, in this case age, is statistically reliable or differentially associated with our outcome. So in this case, age is a reliable and positive predictor of the number of mates that you have. So let's go one by one here and take the exponent of our intercept. So that is the mean of the Poisson distribution when x equals 0. Now, beta 1 then is saying increasing x by 1 unit has a multiplicative effect on the mean of the Poisson by the exponent of beta 1. So, if we wanted to get technical and fancy, this is just showing and proving that, again, a change or a step from x to x plus 1, whatever that is, a 1 unit shift in our x, that 1 unit shift in the conditional mean that is expressed as lambda ends up being the exponent of beta 1. So what we can say then is that if beta 1 is above 0, then the expected count increases as x increases. And if beta 1 is less than 0, then the expected count decreases as x increases. So again, this is very similar to the way in which we would want to interpret our estimated coefficients in any other linear model. In our specific context, though, with the elephant data, beta naught isn't really going to have much inherent meaning because when age equals 0, that's kind of falling outside the range of possible data, right? There's obviously not going to be an elephant that's age 0 and has any mates. Since the coefficient, though, for beta 1 is positive, that means that the expected number of mates increases with age. So an increase of 1 year in age increases the expected number of elephant mates by a multiplicative factor of about 1.07. And again, we get that because we take the exponent of beta 1. Now, we kind of went over this a little bit already, but I want to hammer this point home in how we're exactly getting the fitted values for our model. So the fitted count, let's say for an elephant of 30 years, we would just plug in 30 times our estimated coefficient for beta 1 plus our estimated coefficient for beta naught and take the exponent of that. And so we get 1.61. That means the estimated mean number of mates is 1.6 for an elephant that is 30 years old. What would be the variance? Well, if you said the estimated variance would be equal to the mean, which is equal to 1.6, then you would be correct. Let's do the exact same thing, but now for an elephant of age 45. So instead of 30, we're multiplying beta 1 by 45. Now, when we take the exponent of beta naught plus beta 1 times 45, we end up getting 4.5. So the estimated mean number of mates for an elephant who is 45 years old would be 4.5. The estimated variance would be equal to that as well. So if we want to get not only the predicted values that we just calculated, but also confidence intervals around that, we could use the predict function. So all I'm doing here in line 1 is creating a data frame in which we have age for 25 and 55, or sorry, 25 through 55. And then that's going by every 5 years. So 25, 30, 35, 40, 45, 50, 55. Then we are getting the predicted value. I am then creating in lines 3 and 4 the upper and lower bound based on the standard error that is calculated through the predict function. So what we can see here is that because of that assumption that we have inherently baked in using a Poisson model as the conditional mean, so as lambda increases here, you can see that our uncertainty also increases here, so the variance increases.